Hi folks, welcome to lecture 4. We're going to be going over quite a bit through this lecture, so make sure you have a Word document open, something to take notes with, and you also need to have RStudio open so you can follow along. I'm going to share my screen. Excuse me. All right. Okay, so we're going to go over hypothesis testing, a couple different kinds of t-tests, as well as an ANOVA. So these are different ways that you test your hypothesis. Hypothesis testing is really, just like we discussed before, we're trying to see if our null hypothesis is correct or not, right? And basically you're testing between two samples. So on the bottom, we're looking to see, are these two samples different enough from each other to show that they are statistically different? There's a couple different steps. We determine the type of question being addressed as well as all the variables. We look at the differences between our central tendencies, which you've all learned about. Sometimes we look at the correlation or regression and the differences between the frequency and the distributions. We look at all of this via a mathematical expression. So this is a little flow chart. It guides you through the different questions. Is it a question of either correlations or differences? And then we kind of go from there. A correlation looks at two parameters of, say, a population and try to see if they're related and if they have a positive or negative association with each other. So this is height and weight, and it has a positive association. As something gets taller, it weighs more, so that's a positive association. A regression analysis is when you look at a variable and how it's dependent on another one and what that magnitude is. So it helps us understand how the value changes and the variable changes when the independent variable is also varied. So it has to do with the dependent and independent variables. So a good example is the university GPA is a function of high school GPA. And so you can see that the higher high school GPAs are here on the bottom, the higher the university GPA. And this is a regression analysis here. And so it shows you how the typical value of a high school GPA changes when the university GPA changes when the high school GPA is varied. So when we look at a question of differences, so is it a difference between the distributions, the variances, or the means? Differences between distributions of discrete data tell you that there's some theoretical distribution. A good example is we're comparing data collected of the ratio of men and women from Oxnard, California and Anchorage, Alaska. For testing independence between both these variables, your hypothesis would be, there's no difference between the men and women ratio in between the two cities. If we were testing for the differences between the means, we ask is to see if the mean of one population is significantly different than the mean of the other. So remember, you've learned how to find mean, mode, medians. So you're comparing the means. So the difference between the heights of plants within the control group and the experimental group. We would compare the differences in the means to see if there's a significant difference. Differences in variances. A lot of times tests compare the means of the two populations, and they're assuming that the variances are similar, but there's a lot of assumptions in all of these statistical things where you have to make sure that your variance is equal, your data is normal. We're going to talk about this. So you have to, what they call, satisfy these assumptions. So you can't just start comparing numbers until you do some tests on them. So you have to look at what kinds of questions are you asking and what statistical tests are you going to use. So the different steps, excuse me, I'm going to try to move this up here. The different steps are testing your null hypothesis. And remember, the scientific method just disproves the hypothesis. So if you reject that null hypothesis, it implies that there is some difference or experimental effect. Remember, because the null hypothesis just means there's no difference. When we're looking, if an outcome is typically 95%, then you accept the null hypothesis and assume it's correct. If the outcome becomes 5% of those extreme outcomes, which is that outside edge of the scale, then you reject that null hypothesis. And if this occurs, then you have that alternative hypothesis that there's some difference between X and Y for some reason. So probability is the percentile, so 10% is 0.10, 80% is 0.8. Statistical analysis really calculate the probability or the p-value. And so you'll hear a lot of things about the p-value. It's really the probability of observing that result. So when we assume that the null hypothesis is true, so there's no difference, right? That's the probability. And this is what you see on this chart. So the set of possible results is on the x-axis. Very unlikely is on the ends, and the most likely is here in the middle. If we get a data point towards the outside and that p-value, very unlikely, that means that you usually have a big difference, okay? And we are looking at our alternative hypothesis as correct. So when you're interpreting that p-value, we have the alpha level cutoff, okay, which are these outside errors. That's where you can reject the null hypothesis, or it's really the risk of making a type 1 error, which is accidentally to reject a true null hypothesis. So we set this level here at 0.05 or 5%, the extreme outer 5%. So your statistics have to come into that p equals less than 0.05. So it has to be that extreme outer 5% of the test. Otherwise, you have to say that the null hypothesis is true, meaning that there's no difference, right? So if you get it outside of that, and so it's less than 0.05, that means that there is some kind of difference, something's different. All right. So that's what's considered statistically significant. So overwhelming evidence is this, 0.05 here. Anything above that is weak or no evidence at all. Again, we reject the null hypothesis when it's really low. If it's bigger than 0.05, then we assume that the null hypothesis is correct, meaning that there's no difference. All right. Now we have parametric versus non-parametric statistics, and this has all to do with the kind of data distribution. So do you remember when I showed you the graphs of like the histogram with a nice bell curve, and then some of them are skewed left or right? So non-parametric statistics we use when your data is not distributed normally, okay? And parametric statistics we can only use on normal distributions. So how do you figure that out? Well, we do a test for normality ahead of time. And I'm going to teach you how to do that. So parametric tests assume that data is normally distributed. We, use the sample means and standard deviation. Parametric tests are much more powerful. So usually you get normality when you have more samples, okay? Non-parametric tests are used for abnormal data, or non-normal data rather. So in order to check this, you first do a histogram, okay? And so this is this is the code in R, right? And so this is a normal histogram here on the left, and then this is a skewed histogram on the right. So the rule is, if you're testing for normality and you have samples less than 2,000 samples, you use the Shapiro-Wilks test. If you have more than 2,000 samples, you use the Kolmogorov-Smirnov test, right? I'm going to show you how to do that. So to check if your data is normally distributed, you can also use what's called a QQ plot. So what I want you to do is you have R open. I'm going to do the same thing. I'm going to make my slides a little bit smaller. I'm going to copy this code here. Copy. I'm going to stop sharing, and I'm going to reshare my R screen. Okay, going to go to R Studio, and hopefully you have R up already. Open up an R script, and you are going to paste that code right in there. See how it just pops right in there for you? So then you can run the code. This is saying we're just creating something called normal data. You're telling R to create a set of normal data, normally distributed data, and telling it to also create a set of non-normal data because we want to run a couple different tests. We're going to plot it, and then we are going to create a QQ plot. So You run, is it not like this data? QQ norm, what's wrong? Well, that's rude. All right, if yours works, great. If yours doesn't, don't worry about it. I'm going to show you a QQ plot in just a second. All right, so I'm going to stop sharing. Let's see, stop sharing. Share my lecture screen. Share. Make it bigger. Okay, so don't worry if it doesn't work right away. I probably need to fix the code. But a QQ plot looks like this. So basically the plot is these dots here, and then you put a QQ line. So this is pretty normal. See how most of the dots are along the normal line, and this is non-normal. So where these dots, so many of them don't touch this normal line. Okay, so it's just another way to kind of look instead of a histogram, you can make a QQ plot. Or both. You always, always, always have to test for normality. You cannot just run your data and assume it's normal. If you do, it doesn't count. Again, always, always test. You have to make sure it's a, parametric test. If not, you use a non-parametric test. All right, so if you do the same thing, you can grab this code here. You grab the create data. Oops, go back. So this is the Shapiro-Wilks test. Again, if it's less than 2,000 samples, you can grab this data here, plug it into R and run it, and you will get this at the bottom, which is called the Shapiro-Wilks normality test. W, don't worry about that, but your p-value is 0.09. So that's higher or lower, right? It's higher than 0.05, so that means that the data is normally distributed, okay? So I know this is a little funky and it's a little hard to remember everything. So you might want to make yourself some notes. Like if my p-value is above 0.05 in a normality test, then it's good, it's normal. If it's below, that means it's not normal. Okay, and you need to pay attention to these things and write down little details. Here is the normality test if we have a huge sample of over 2,000. So you can copy this and you can put it in R and run it if you want to see what happens. This is what comes out of it. The p-value is 0.67, so it's higher. So that means that for this particular test, that the data is also normally distributed. It's a different kind of test. So for this Kolmogorov-Smirnov, this is why I say you need to make yourself like a chart or just some notes to read, because I always have to go back and look like, shoot, which test is it that means the p-value is this or that. I always double check because I can't seem to remember or memorize this stuff. If you can, awesome, but I never do. I have a chart, especially when I'm doing my own statistics. All right, so now we're going to talk about a couple different kinds of t-tests. So one sample t-test is when you're comparing the sample mean to like a hypothetical population, okay? So is the height of students from my class the same as the population mean of 60 inches, right? For all of Sisaki? I don't know. Well, let's see. The mean for our class is 50 inches. Standard deviation is 8, and there's only 15 students, right? So N is the number of samples, SD is standard deviation, and X is the mean, or sample mean, rather. But one sample t-test is a little bit limited, okay, because you're just comparing it to like a hypothetical population mean. So no one really, you can do that, but you're not going to probably do that. So really what we need to look at is we want to compare two different samples, right? So we're going to, a one sample t-test is still limited, but we can draw from the same population, all right? So let's look at this. If you want to figure out the mean of certain species of plant that are equal to 15 inches. This botanist is going to collect a random sample of 12 plants and she goes ahead and records each of their heights in inches. This is a link that you can click on that will go through the R code and more explanations for you. I tried to put some of these in here to help. So one sample t-test, go ahead and grab this. So first you have to create the vector. So meaning you have to create like a data set instead of uploading a CSV file or an Excel file. So how you tell R to do that is you type in my data, or you can name it something else, and you tell it to, sorry, remember I'm at home, so I have cats. jumping across the things. And basically you're just telling R that these are your data numbers here. And then to test it is t-test my data, comma, mu equals 15. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What was 15? Let's go back and look. 15 inches. We wanted the height of a certain species equal to 15 inches. Okay, so you run your data, your one sample t-test comes back. T degrees of freedom is usually one less than the number of samples that you have. Your p-value is 0.12. So what does that mean, right? So let's look and see. So this gives you the confidence interval, which is that 95%, the part of the big bell curve, okay? And this is how we get our one sample t-test. So the true mean is not equal to 15. So this means that we will reject the null hypothesis and accept the alternative hypothesis, okay? Because basically the botanist was saying that she figured that the sample sizes would be, the mean of the sample sizes would be 15. And with these plant heights, they are not. That's not true. So then we have a two sample and paired t-test. So two sample t-test is to compare two sample means, okay? So we're assuming that each group is from a population and each group is independent of those in the other group and everything is normally distributed. So think of the purple sage example. So we're walking along Water Canyon and you collect, you're collecting measurements or flower numbers or something from each plant. Then you're taking them all on one side and all on the other. So you know, or halfway down. So you, and an even number. Okay. So distinct populations, we're gonna compare them. So what if you violate the assumptions? And what I mean by the assumptions, remember, is that distinct populations, they're independent and they're normally distributed. Okay. If you violate them, meaning that if you don't test for it, your t-test doesn't matter. You can't use that information. You have to use the non-parametric tests. Okay. And then you just use a different kind of ranking test. And here's some links on some of those as well. So the two sample t-test, this is the math behind it. Okay. You're doing the sample means divided by the number of samples minus 1, which is degrees of freedom. Okay, you do not need to remember all the math, but I want to show it to you. Okay, so basically the numerator shows the difference between the sample means, and the denominator shows the standard error of the difference between the two. Okay, here's the degrees of freedom, sample plus sample 1 plus sample 2 minus 2, because there's two numbers, because degrees of freedom is the number of samples minus 1. That is something you should remember. A two sample t-test is a little bit different. You're again looking at the difference between sample means. This is if the variances are unequal, and I'm going to teach you how to figure that out as well. So first, for our two sample t-test, this is the code up here. T-test, group 1, group 2, the variance is equal equals true. So that means that you're assuming that the variance is equal, okay? And I'm going to teach you how to figure that out in a second. But if you tested it and the variance was not equal, you would write variance equal false, okay? And that's how you tell R to say either it is or isn't, okay? We're going to create two groups of data and perform the sample t-test. You can just copy this code. It's a whole thing. All the blue ones are code. And you can, the bolded stuff here is great to put into R because then it tells you what you did. It should pop out saying two sample t-test data. You have group 1 and group 2. The degrees of freedom are 22, so that would be all the samples minus 2. Your p-value is 0.01, okay? So that means that the alternative hypothesis is true because, excuse me, it means that there is not equal to 0, meaning that those two samples are different. So when you're running a t-test and your p-value is less than 0.05, it means that there is a difference, okay? So a one sample t-test is used for comparing a sample mean to like a big population mean, and a two sample t-test would be independent, or it's called an independent t-test, okay? Comparing two sample means. So you'd be taking two samples of that population and then comparing them together, all right? So one sample is when you just have like a group like the kids in class, we measured everybody's height, and then we're going to compare it to what we assume is the whole population height of CSUCY. Or a two sample t-test would be like all the kids in this class and then all the, sorry, students in another class, okay? And those would be two separate samples within the same population. Here's another example, all right? You can use this even if to test whether or not those means are equal, all right? Because you want to see if there's a difference. This is the basic, what we call syntax, okay? So this is the code right here in the middle. Oops, sorry. This is the code, t-test, group 1, group 2, variance equal, which is true. We are assuming, we're telling R that the variances are equal, okay? If you don't want to make this assumption, you would just do t-test, group 1, group 2, and then the parentheses, okay? So it means that you would not assume the variances are equal. And I know this kind of sounds crazy, okay? And it's a lot, and I know it's a little overwhelming, and you're probably not going to remember everything, but if you need to pause the lecture, pause it and write stuff down. When I write code for t-tests, if I assume the variance is true, which she hasn't even told us what that means yet, okay, then it will perform a Welch's t-test, which R automatically does it. All you do is you either write that the variance is equal or not, but I will show you in just a minute how to figure that out. So here's our group. You can pop this in. Here's our 12 plants from each species. Here's the group. Here's the codes. Okay. And then over here on the right, this will be our differences, right? And here's the p-value. So the true difference in means is not equal to 0, meaning that it is different. And that means that the population is different. Okay. So let's go over this just a minute. All right. Two sample t-test is an independent t-test. You have to see if it's normally distributed. In order to do that, use Shapiro-Wilks if it's a smaller than 2,000 samples. If it's larger, you use this other one. You also have to test if the variance is equal because there are different what we call T equations. So now I'm going to teach you how to test for the equality of variance. So it's called Levene's test. All right. So a lot of tests, like ANOVAs, which we're going to talk about this in a second, the assumption is that the variance is equal, but you really should always test this to do statistics properly. All right, so Levene's test is to see whether or not the variance between those two groups is equal, right? So the null hypothesis is that the variance is equal, and the alternative hypothesis is that it's not equal. So that means that the p-value from the test is less than 0.05. We reject the null hypothesis and conclude that we have enough evidence to state that the variance among groups is not equal. So you want to have equal variance for certain tests, but if you don't, you have to run a different one. So it's not good or bad data. You just have to pay attention to what you're getting, right? So the variance is equal if P equals 0.05 or more. It is not equal if the p-value is less than 0.05. Okay, you can write that down. So how do we do this? So in R, we use the code Levene test parentheses function, and it's from the CAR library, which uses this syntax right here. So the Levene test, you have a response variable and your group variable, and then data equals data. This just means that this is what it's reading, okay? I will talk about these other variables in a second. So let's think about this. How much weight was lost on 3 different weight loss programs? Okay, we're going to look at this data. We're going to put in real quick here is set the seed. This just makes it reproducible. Then you're going to copy and paste this code. We're calling our data. That's what we're naming it for right now. And then this arrow and dash tells us that the data frame, which is basically R's way of looking at an Excel sheet or anything else, but we don't have one, so we're going to make one up. So we're creating a data frame and we're going to call it data. So you're going to write program equals, but don't write this on your own. Just copy and paste this. And what it's doing is these 3 numbers talk about weight lost, okay? So here, and then I want you can view the data by clicking head, and then writing data here, and this should show you the first few rows. All right, so we're going to run this Levine test. Trying to make this easier for all of you. Before you run the test, you're going to need to copy and paste install packages for car and library car. And then you're going to conduct this Levine's test. So weight loss and program, remember what those were. Let's go back. So response variable is weight loss. Okay, so it's responding to the test. So the group variable is the weight loss program, right? Yes, weight loss program, and weight loss is the response variable. Okay, so that's really important to pay attention to, and you will learn and you'll get better at this as you practice, which we're going to do this week. So when you go to report it, this is what pops out in R. It looks over the center medium. It gives you kind of a table like this, and your p-value is 0.01. So that is less than our significance level of 0.05. So that means that we reject the null hypothesis and our groups are not equal. So there is not equal variance. And that's okay. We just have to do a different kind of test. So when we have a paired t-test, this is a slightly different kind. It's when your data are matched. So you don't want to be making a type 2 error saying that there's no difference when there actually is one. All right. So you would use a paired t-test, like if you're measuring samples that are related to each other or measured twice. So say, let's see, you're taking heart rate before and after caffeine consumption. All right. So you have 10 students, you measure their heart rate, then you have all of them drink like a cup of coffee or a cup of soda or something with caffeine. And then you wait a certain amount of time and then you measure their heart rate again. So that's what you would call a paired t-test because you're doing samples that are related or measured twice. All right. We assume that the differences between the pairs are normally distributed. It gives you a lot more power to detect the difference between these samples. So say this is you could even take this data if you want and check it out. So here's our 10 students, here's the heart rates before, and here's the heart rates after. These are the two means. Okay, so we're going to test the difference between the two means. Okay. Oh, here it is. All right. And so we get our p-value of 0.001. So we're rejecting the null hypothesis, meaning that there is a difference between their heart rates before and after a cup of coffee. Okay. A paired sample t-test. This is a link that you can click on for using R. All right. We're going to do an example to see if a study program impacts students on a test. So we have 20 students take the pre-test, then we have each of them go into the study program every day for 2 weeks, and then they retake a similar test, right? And we compare the differences between those. So that's paired because it's a resampling, okay? So how we conduct this, we use the following approach. Our null hypothesis is there's no difference, and then our alternative hypothesis is that there is a difference. There is a difference. There is a difference. It'll either go up or it'll go down or it'll be a split. So the next step to that is finding our test statistic. Wow, I can't really talk today. A will be the student's score on the first test and B is on the second test. And our null hypothesis is that there's no difference between the tests, that the study group's not going to make any difference. So these are all the math pieces behind this, okay? And we're going to reject or fail to reject that null hypothesis based on this significance level. All right. So this is our R code, okay? T-test XY paired equals true, and alternative is two-sided. All right. So X and Y are the two numeric vectors that we're comparing. So the before and after scores. Paired is that logical value saying that we want to compute a paired t-test. Okay, because see how this first code here is t-test? We have to tell it to do a paired t-test, otherwise it's going to do a regular one, and that's not going to work. And then the alternative hypothesis, you can set it to two-sided, which is the default, or greater or less. All right, so if you think that it'll be bigger or less. So now we're going to see what our test looks like for those 20 students. So over here on the left, you can copy this code, all right, and pop it in there. Go ahead and do that. Then on the right, you're going to have to install a new package. It's called the Dippler package. Go ahead and install it with the library. So just copy and paste all of this all the way down to this last little weird parentheses. No. Yes, parentheses. I think I need more coffee today. And pop it in there, and we're going to look at the summary statistics, okay? So group by and summarize are these different functions that we're going to use from this library, all right? You can also create some box plots, which this is the link to go through this if you want to see it. Go ahead and copy and paste this data in, and you'll get to see some box plots to show some charts and graphs from your pre and post group, okay? Then we're going to conduct the paired t-test. So you can check and see if your differences are normally distributed. So we can create a new vector between the pre and post scores so that we can check that Shapiro-Wilks. So what you're going to do is copy this and write differences. That's just the name of it. And you're going to call this with data, that's the name of your data, score group equals post, and then also score group equals pre. So this is telling it to split the data between pre and post scores, and then to perform the Shapiro-Wilk test on the differences data. All right, so this code here is splitting the two data groups, this top code here. And then this code is just saying to run the Shapiro-Wilks test, which is the normality test, on the differences. So the p-value is 0.1135, which is greater than our 0.05. So that means that our data is not normally distributed, right? Let me see. Yes, this means we can, yeah, so it is normally distributed. Sorry, I always get that mixed up with the t-test and the differences test, or excuse me, the normality test. So right, we want it to be above 0.05, and then it is normal. See, that's why I write everything down. Okay, so now you can do the paired t-test. So t-test is score is our, which variable, right? This is our, can you remember? Okay, there's gonna be a question on this. Group, and then data is data, and paired, because we want it to be a paired t-test. This will be your output. P-value is 0.12. So the alternative hypothesis, the true difference in means is not equal to 0. So that means there is a true difference in the means. Pretty cool, huh? I know this is a lot, and you're like, yeah, whatever, Dr. Horn, this is just tons and tons of stuff. Take your time, pause my talking, pop the data in R. All right, we get the T statistic, which is 1.5. We get our p-value with 19 degrees of freedom as 0.12. This 90% confidence interval is here, and our mean difference between the pre and post group is 2.15. So our p-value is less than our significance level, so we fail to reject the null hypothesis that the two groups have statistically significant means. Okay, well, that's a lot of words. Basically, we fail to reject the null hypothesis. That just means that we are saying that the null hypothesis is true, that there is no difference. So when the p-value is greater than 0.05 in a t-test, it means that you say the null hypothesis is true. That means there's no difference, okay? It's just that in science, for probably some old white dude decided that we have to write, we will fail to reject the null hypothesis. Let's put 8 negatives in one sentence. But just remember this, when you do a t-test, if the p-value up here is greater than 0.05, that means there's no difference. There's no significant difference, all right? And then you can go back and look at all the googly glop science stuff, and you can write it out that you fail to reject the null hypothesis, okay? In addition, our 95% confidence interval says we're 95% confident that the true mean difference between the groups is somewhere between negative 0.6 and 4.9. Well, the difference is 2.15, so okay, good. And since the value 0 is contained within the confidence interval, it means that 0 could also be the true difference, okay? So basically, if the test is telling us that our difference is somewhere between a negative number and a positive number, it means that it could be nothing, right? It could be 0. That's what all of that is saying. When we're comparing two samples, the first thing we do is check to see if it's normal distribution or not. And there's two tests, right? If you don't have normal distribution, you have to use what's called a non-parametric test. And that's okay. There's nothing wrong with that. It's just usually not as strong. If our data are matched, we use a paired samples t-test. So you have to make sure that you tell R to pair that t-test. All right. And if they're not matched, meaning it's not like a before and after type of a sample, then you can do the independent two-sample t-test. A paired t-test, we talked about this like 5 times already. If you don't do a paired t-test when you have matched data like that, it's creating what's called a type 2 error, and you're messing up your statistics. It's not good. When you're comparing, oops, nope, go back. When you're comparing two samples, you want to make sure you always perform the appropriate t-test. The f-test is the two samples for variations. So you also need to make sure that the variances are either like equal or not, and you have to interpret the results. So p less than 0.5, meaning that the samples are not equal. P greater than 0.05 means the samples are equal, okay? Means there's no difference. So just remember to write little codes down for yourself. This is from an old paper, but it's not a terrible graph. So when you have a question and say you're going to see if there's a difference between something, you do the between variances is an f-test. Okay, so we just learned that. Between means, you go down here. Do we have two samples? Okay. Is it a parametric test? Okay, that means that it's normally distributed. If it's not, it's non-parametric. You can do this other rank sum test. Say you have more than two samples. I'm going to teach you how to do an ANOVA right now. And this kind of helps you walk through a couple of the different tests. All right. We're going to also talk about correlations and regressions, but not until the next lecture. So we'll talk about that next time. Last but not least is the ANOVA. So this is just more samples. So it means that you have multiple variables. One is categorical, which what is that? What's categorical? Oh, that's right. Like cars, right? Colors of cars is categorical, or types of animals in the park. That's categorical. Okay. And quantitative is numbers. All right. The main question is, do the means, the middle, right, of the quantitative variable or the counted variable depend on which group given by that categorical variable the individual is in? So what does that mean? So so what would be an example? So quantitative is a count of something, a count of the category. Oh, so maybe like 10 yellow cars, 12 pink cars, 17 white cars. Does that make sense? Okay. If the categorical variable, meaning the cars, right, only has two values, so like white or yellow, you would do a two sample t-test. But we know that cars come in way more colors than that, right? So yellow, green, blue, brown, yellow, white, whatever, ANOVA. Okay, so anything more than 3 groups means that you have to do an ANOVA. You can't do a t-test. Doesn't know how to do that. So for an example, all right, we have 25 patients with blisters. There's 3 different treatments. So treatment A, treatment B, and then a placebo. That sucks for the placebo, right? The measurement we're looking for is the number of days until the blisters have healed. So in treatment A, we have 5 days, 6 days, 6 days, 7 days, 7 days. Okay, does that make sense? See, so these are our categories, A, B, and P. And this is our quantitative measurements, 5 days, 6 days, 6 days, 7 days. Okay. So now we want to know are these differences significant, right? Like, are the treatments better than each other, or is it just like the placebo? So an analysis of variance is the mean of A equal to the mean of B equal to the mean of C. That's our null hypothesis, that there's no difference, or our alternative hypothesis is that they're not equal, but it doesn't necessarily say which one is better. We're just going to follow up and see which one is different. So analysis of variance is an ANOVA. It's a parametric statistical test of differences between the means of more than 2 samples. We assume that our observations are independent, meaning they come from a continuous scale of measurement. They are normally distributed, and the variances of those samples must be homogeneous. So our null hypothesis is there's no difference. Analysis of variance is something like this as well. So you have a population of purple sage, and we're taking 3 different samples, like a mile in between each along Water Canyon. Our null hypothesis is that there's no difference in their height. Here's some notations for ANOVA. You can always write these down, make a little note for yourself. N, again, is the number of individuals. L is the number of groups. X is the mean for the whole data set. Group I is the number of individuals in each group. So number of individuals, and the little I is number of individuals in the group. Xij is the number of individual j in each group I. Okay, I know this is a little goofy, but standard deviation is Si. X lower I will be the mean for the group. You'll see this in the math that I'm not going to make you do. All right, how does an ANOVA work? So we are looking at the variation between the groups for each data. So that how we figure that out is we look at the difference between its group mean, so each little mean, and the overall mean, okay? We also are going to look at the variation within each of the group for each data value. We want to make sure that the value is, the difference is between the value and the mean of its group. I know this sounds a little crazy, but just give me a second. We're going to show you, okay? So these are a couple of little box plots that you can do in R. I did box plots for you, I think, already, but maybe we're going to do that in the next, I think we're going to do that in our worksheet this week. So treatment is down here on the x-axis. So treatment A, treatment B, and the placebo, and however many days it took for them to heal. And you can see that this midline right here in the box plots, that's the mean. So what you're doing is you are comparing the amount of variation, so from the top to the bottom, that's the variation between each group, and then the variation within each group. I know that sounds a little funky, but you're looking at these lines, the means, okay? So the F statistic is the ratio between the group variation divided by the within group variation. That's just, so a large F is evidence against the null hypothesis. So the bigger the F means that there's a difference. There's a really good difference in between. So remember, the null hypothesis is that there's no difference. So you want a high F value if you're trying to show that there's a big difference. If you're trying to show they're all the same, the lower F value is going to give you your null hypothesis, which is there's no difference. So how do we make these computations? For each data value, we calculate its contribution to group variation between and within. In R, it's a little bit different because you have to write the code. So again, here's the link to run a one-way ANOVA. So we're going to create some data. Suppose we want to determine if 3 different workout programs lead to different average weight loss in people, right? So we recruit 90 people and to participate in the experiment, and we randomly assign 30 people to follow program A, 30 to follow B, and 30 to follow C for 1 month. Let's make this example work. So I want you to copy and paste the left side of the data. Set C just makes it reproducible. Here's your data frame. Just go ahead and copy and paste this in there. Then you're going to use the AOV command, which is how to perform an ANOVA. You're going to copy and paste this. This says fit one-way ANOVA model. You're going to copy the part that says model because that's what we want it to create. The arrow AOV is telling it to run an ANOVA, which is the weight loss, right? And the program group, and data is data because that's our name over here. See, we created the data frame first because I didn't want to give you an Excel sheet. So I'm trying to teach you how to do things slightly differently. You will notice that when you copy and paste this part that says create data frame into R, and you click run, all 4 or 5 lines will run at the same time. That's what it's supposed to do. All right. So now we're going to get some results, but it doesn't just pop up right away. So you have to tell it to. So go ahead and copy and paste view summary of one-way ANOVA model. You're going to tell it to give you a summary of the model. All right. And this is what pops up here. So you have degrees of freedom, which is 2. You have the sum of squares, mean squares, your F value, and your P value. So your F value is 30.83. Your P value is real negative. Okay, so that means that it's very significant. The residuals are something that you would graph later on. I'll teach you how to do that as we go forward. But for right now, we'll just follow along with this. So here's how we interpret the output. All right. DF is the degrees of freedom for the variable program. This is calculated as the number of groups minus 1. So there's 3 different groups, so it's equal to 2. degrees of freedom for the residuals is calculated as the total observations minus the groups. So there were 90 observations and 3 groups. So that's why that value is 87. The sum of squares is associated with the variable program, that's 98.3. The sum of squares with the residuals is has to do with the errors, and you can graph your residuals and your errors. That's something that you'll learn to do as you get better at statistics, okay? And that's 139.7. And then mean square program is the sum of squares of the program divided by the degrees of freedom of the program. And so it's calculated as 98.93 divided by 2. All right. I'm just trying to explain to you what all these things are, and you have all of these slides. The mean square residuals is the same. The F value, in this case, it's calculated as 49.46 divided by 1.6, so that's 30.83. And our P value is associated with the F statistic as the numerator, so degrees of freedom equals 2, and the denominator is 87, so 2 divided by 87 is a super, super low number, super tiny number. However, the most important value is the p-value that you're looking for, because it tells us whether or not there's a significant difference in the mean values between the 3 groups. And when the p-value is less than 0.05, it means there is a significant difference. So the alternative hypothesis, remember, is that they're all equal. There's no different. Our alternative hypothesis is that at least one group is different. And since our p-value is less than 0.05, we have enough evidence to reject the null hypothesis, or saying that we have sufficient evidence to say the mean weight loss experienced by the individuals is not equal between the 3 workout programs. So this slide right here, I want you to pay attention to, because in our review exercises, you are going to have to report your data analysis, and I want you to be able to make sure you write out sentences like this, okay? So make yourself a little note to make sure to look at this, and all the slides are posted, okay? If we have to perform what's called a post hoc test, because the ANOVA told us that the groups are different, but we don't know what the groups are, what the difference is between each group. Does that make sense? So we don't know which group they lost the most weight, etc. So in order to find this out, we run what's called a post hoc test. In R, it's called the Tukey HSD. So go ahead and you can copy and paste this into R and run it on the model. That's the name of our ANOVA that we ran, and it should pop out like this. So we have all the numbers here for B, the difference between B and A, C and A, and C and B. Okay, so that's what all this means. So here's how we interpret the results. The p-value between group A and B is 0.01, so there's a difference between that one. The p-value between A and C is 0, so there's a difference. And the p-value between B and C is 0.000. So since each of them are less than 0.05, we can say that there is a significant difference in weight loss between each group. Okay, so we went over types of data, descriptive statistics, we've been over variability, we've gone over hypothesis testing, and then in the next lecture, we'll talk about correlation and regression. So I'm going to give you a little quiz and some questions. You get 3 tries each. There is no time limit. Remember that you have all of these slides set aside in a PDF, so you can open them and go back and review. And these quizzes are here for you to like really put it in your brain, not to assume that you memorize this just because I was talking at you. Okay, good luck, and I look forward to your answers.